Good morning, dear colleagues. Please take your seats. It's a pleasure for me to introduce session 3 of this wonderful conference this morning, which is going to address a specific subject that was presented by Jean-Jacques Dordain yesterday, which is how to go back to the moon while taking care of the environment as we do now, or try to do on Earth. So going to the moon is, of course, the next and first step in exploration, and we believe we have to do it right. So on this introductory cartoon, I will just show what is the logics of this session. We are going to meet the environmental challenges of lunar exploration. And we have a sort of a slogan: let's build a virtuous circle of lunar exploration. Of course, we want to study the lunar environment, to understand it. We want to utilize it, but at the same time, we want to mitigate the effects of our activities on the lunar environment. So our session is all about that, and we are going to actually explore together this virtual circle. So we will start by moving from understanding to utilizing, and then we will go to mitigating. So understanding, I will do the first presentation about the lunar environment, the scientific assets, the cultural heritage to be preserved. And then we will explore with Dylan Maxwell the assessment of the lunar resources. Where are there resources on the moon to support our activities on a permanent basis? Then Jerry Sanders will talk about utilization and, in fact, what we call in situ resource utilization. After a half-hour first panel, moderated by Bernard Foin, that will address the question of the development of activities in this new wave of lunar exploration, we will go to the exploration of different ways for the mitigation of effects on the environment. So Eric Joffre will talk about the management of lunar orbits, how to do that cleanly, how to recover the safety of the orbits, what to take care about the different types of elements that will remain in orbit. Alexis Payet will manage the surface of the moon, if I may say. He will tell us what are the ways to mitigate the effects on the environment of the successive activities. And finally, Antonino Salmeri will introduce something which I think is very important, which is the legal framework within which all activities on the moon will have to develop. So with that, let me just go to my own presentation, which was prepared with my colleague Pierre Melin from IRAP, my laboratory. Pierre is the PI on the Dawn experiment on Chang'e 6, so a mission which is going to fly to the moon in about 2 years from now, and that will study radon emissions at the surface. I also want to thank warmly all my colleagues here who have been providing elements for this short presentation. So first, let's say that some people may think that moon science is an old science since it started in the 60s, 70s. But let me say, I think all to the contrary, moon science is a very modern, hot, and vivid issue now, because we can put it in a broader context, which is the science of the moons in general in the solar system. So here I have shown the sort of family portrait of moons of the solar system. And of course, we know the moons of Jupiter, Saturn, the other giants. Even Mars has 2 moons. And in fact, it's really a vivid subject of research. Cassini-Huygens has been studying, of course, Titan, but also Enceladus, this very tiny moon, which was found to be so surprisingly active. And right now, we are exploring the Jupiter system with Juno. Juno is actually preparing for 2 flybys of EO by the end of this year and next January. Scott Bolton, the PI of Juno, is here, and you can talk to him if you are interested. But even more than that, JUICE has just been launched and is on its way to the Jupiter system and Ganymede. Our colleagues at NASA are preparing Europa Clipper that will be sent in about a year and a half to the Jupiter system, and will do many flybys of Europa. And finally, I wanted to mention that in the Chinese Deep Space Exploration Program, Tianwen-4, will address Callisto. So you see, we are a place to really develop a comparative approach of moons of the solar system, or even beyond, because let me see, one of my great expectations is that very soon we can discover exomoons around giants in our galactic neighborhood. The technology to do that is on its way, and I think with the transit time variation, it will be very soon possible to do the first, let's say, detection and actually discovery of an exomoon. So in this context, let me say that actually the Earth-Moon system is something really unique, and it should be understood as such. The Earth-Moon system has unique characteristics, among which I would like to mention that, in a way, this system is made of two terrestrial planets of about the same size. That is unique. The moons of Jupiter are only 10 to the -4 the mass of Jupiter. Here we have two similar objects. Second point, we believe from theory, modeling, and observation, in particular from the Apollo program, that the moon was formed from a giant impact with another terrestrial body during the formation of the solar system. That is certainly unique and makes the moon sort of the sister of Earth, where we can do complementary studies to understand our own planet. And finally, we know that the moon had and has a strong influence on Earth's evolution, its habitability, the stabilization of its spin axis in particular, and therefore the seasons, and even the climates. So it is such an important object where we have to go back. And of course, going there means doing science. I think it's the first perspective that I will draw now. So what we are going to explore in terms of science? First, let's say it is a system, and it's a complex system with different scales, 3 scales. First, we have to encompass the global scale of the system scale. What is characterizing the Earth-Moon system, in particular for people like me who are doing magnetospheric science, the moon along its orbit is traversing very different plasma regimes in the solar wind magnetosphere interactions. Here, on this side, the moon is in the solar wind, then we cross what you call magnetosheath, and we go into the magnetotail and back. So the moon is a fantastic place to study plasma interactions in the solar system. But then let's scale down. The second size or scale is the planetary scale. The moon is a small terrestrial planet. It's a template of a terrestrial planet, and it's an accessible one where we can do at the surface all the types of measurements that we do on our own planet to understand, in particular, its working, its history, its interior, its geology. So that's a fantastic opportunity to do that, and the new wave of exploration will, of course, develop that. But since we are talking today about the lunar environment, let me mention what I call the lunar environment. It's actually this tiny layer here where the regolith of the moon is interacting with a very tiny atmosphere, in fact an exosphere. And that's where the astronauts and the other visitors of our satellite will live at the surface and in the near orbit. So we need to really understand this lunar environment and how it will be transformed by activities from humans and from robots. So first, let me say that the first thing we need to realize when we go back to the moon is that the moon is a fantastic, unique place for deploying at the international level a unique pluridisciplinary observatory. At the moon, looking down, you can sound the moon's interior, where, for instance, by deploying a network of seismometers, you can read the history of the solar system from the measurements of the rocks. You can study solar wind heliosphere interactions. But we can also look up into the sky, and there you can open new windows into the universe, in radio astronomy, for instance. You can monitor Sun, Moon, Earth interactions. You can observe the Earth and its climate system. It's a good vantage point for study of our own planet. So the main message I put here, planning for the step-by-step deployment of a multinational moon-based research infrastructure, what the European Union calls the research infrastructure, is very important. So on the moon, we are not doing just single scientific experiments. We are deploying a research infrastructure. And that makes a very big difference and puts responsibility on us. So it's a unique opportunity for science and an urgent task for the scientific community across all borders to build together something that will make sense scientifically and will return the maximum amount of science and new knowledge from this new phase of lunar exploration. So let me just say what I mean by the lunar environment. In fact, the plan associated with the new wave of lunar exploration, in a way, is to say we have our Earth environment here, our ecosystem where we live in balance with the nature. We are going to extend through Moon-Earth orbits this place of living for humans to this small layer here around the Moon, where new activities will develop. So we really need to understand that we are planning to extend our own ecosphere from the Earth environment to the Moon environment with connecting places. So that's what we want to do, and in order to do that, of course, we need to know what are the natural resources that can be used for this purpose. So let me say, the lunar environment is subject to 3 types of forcing that I will review very quickly. First, internal forcing. Tectonism, volcanism impacts over the long terms has been shaping the diversity of lunar terrains. You can see here to the left the extreme variations in the crustal thickness from the very thin crust we have near the South Pole Aitken Basin, where Charlier 4 landed, and Charlier 6 will land also and return samples, to thick layers corresponding to the oldest parts of the lunar terrains. Looking at geochemistry, a tracer like thorium also shows you the presence of very different geochemical provinces. So all that is to be explored, and all that is reflected in the diversity of terrains where we will live on the Moon. Then the second thing is external forcing is also acting on this fragile environment. Meteoritic bombardment, the solar wind, cosmic rays, what we call space weathering, are actually sort of breaking the original bedrock on the Moon, and with time, but there was a lot of time, billions of years, it produced this complex layer of the surface of the Moon, which is called the regolith. Over time, the regolith moves from what we call immature to mature and changes its color. Then the regolith is also interacting with the lunar exosphere, which is actually an expression of outgassing of the regolith and interaction with the space environment. So we have to understand how this complex coupling between regolith, lunar exosphere, and the space environment works. And finally, a very important point is a new perspective, is that lateral motion, lateral transport of volatile species in the exosphere transports, in particular, H2O, water, to the potential cold traps in what we call the permanently shadowed regions. So there, near the 2 poles, there may be places where a lunar cryosphere has been developed, and of course, this is an essential element to find resources, since water is always the first resource you are looking for if you want to survive somewhere. So the third type of forcing on the lunar environment is human forcing. That's what we are going to do now. Human forcing is going to do a lot of things that we need to understand. Alteration of the lunar exosphere, for instance, by traffic-related propulsion, the plumes from the landers, surface activities, all types of surface activities, contaminations of the surface, of many different types we have to understand. And finally, pollution of the electromagnetic spectrum that will impact astronomy, and if we want really to use the moon for astronomy, we have to take care of that. This is just an example of a simulation which shows the effect of the plume of the Apollo 17 lander, which basically ejected several tons of H2O and other elements